Torch, split. Description. The torch, split function divides a tensor into multiple subtensors along a specified dimension. It provides a flexible way to partition data for parallel processing, data analysis, or model training. Inputs. Tensor. The input tensor to be split. This is the tensor that will be divided into subtensors. Split size or sections. This argument specifies how the tensor should be split. It can be either an integer or a list of integers. If it's an integer, it represents the size of each subtensor along the split dimension. The tensor will be divided into as many subtensors as possible with this size. If it's a list of integers, each element represents the size of a corresponding subtensor. The length of the list determines the number of subtensors. The sum of the elements in the list should be equal to the size of the input tensor along the split. Dimension. Dim. The dimension along which to split the tensor defaults to 0. The first dimension. Outputs. A list of tensors. Each element in the list is a subtensor resulting from the split operation. Steps. Tensor preparation. Ensure the input tensor is the correct type and shape. Splitting. The torch, split function performs the actual division of the tensor based on specified split size or sections and dim. Challenges and fixes. Uneven splitting. Sample use case. When the size of the input tensor along the split dimension is not divisible by the specified split size or sections, the last subtensor may have a smaller size. Fixes. To ensure all subtensors have the same size, you can use a split size or sections value that is a divisor of the input tensor's size along the split dimension. If you need uneven splitting, be aware that the last subtensor might be smaller than the others. Invalid input. Sample use case providing an invalid split size or sections value, e.g. negative values. A list with elements that sum to a value greater than the input tensor's size can cause errors. Fixes. Carefully choose the split size or sections value to ensure it is consistent with the input tensor's size and the desired splitting behavior. Verify the input values before calling torch, split to prevent errors. Splitting along incorrect dimension. Sample use case providing an incorrect dim value will result in the tensor being split along an unintended dimension. Fixes. Double-check the dim value to ensure it corresponds to the desired splitting dimension. Remember that the default value is 0, which splits along the first dimension. Torch squeeze. Description. The torch, squeeze function removes singleton dimensions with size 1 from a tensor. It is a useful function for reshaping tensors and preparing them for operations that require specific dimensionalities. Inputs. Input 1 input, a p-torch tensor with potential singleton dimensions. Outputs. Output 1 output, a p-torch tensor with the singleton dimensions removed. Steps. Step 1. The torch, squeeze function identifies all dimensions in the input tensor that have a size of 1. Step 2. It removes these singleton dimensions, effectively collapsing them. The resulting tensor has the same data as the input tensor but with reduced dimensionality. Challenges and fixes. Challenge 1. Removing a dimension that is not a singleton. Sample use case that resulted in challenge 1 trying to remove the first dimension of a tensor with shape 2. 3. Using torch, squeeze input 0. Fixes to challenge 1. Torch, squeeze can only remove dimensions with size 1. To remove other dimensions, use torch, reshape or torch, permute. Challenge 2. Removing a dimension that does not exist. Sample use case that resulted in challenge 2 trying to remove the fourth dimension of a tensor with shape 2. 3. For using torch, squeeze input. 3. Fixes to challenge to the dim argument in torch, squeeze specifies the dimension to remove. If the specified dimension does not exist, no dimension is removed. Ensure that the provided dim argument corresponds to an existing dimension in the tensor. Torch stack. Description: the torch stack function is a fundamental p-torch operation that combines multiple tensors along a new dimension. It takes a sequence of tensors as input and stacks them along a specified dimension, creating a new tensor with an additional dimension. This is particularly useful for combining batches of data, manipulating sequences, or creating higher dimensional representations. Inputs. Input 1: a sequence of tensors, which can be a list or tuple. Each tensor in the sequence must have the same shape except for the dimension along which they are stacked. Input 2: the dimension along which the tensors are stacked, specified as an integer. This value indicates the index of the new dimension in the output tensor. Outputs. Output 1: a single tensor that results from stacking the input tensors along the specified dimension. The shape of the output tensor is determined by the shapes of the input tensors and the stacking dimension. Steps. Step 1: the torch stack function gathers the input tensors and aligns them based on the specified dimension. Step 2: a new dimension is created along the given dimension index, and the input tensors are arranged within this new dimension. Challenges and fixes. Challenge 1: mismatched tensor shapes. If the input tensors have different shapes excluding the dimension along which they are stacked, torch stack will raise an error. Sample use case that resulted in challenge 1: attempting to stack tensors with different numbers of elements in each dimension, except the one being stacked. Fixes to challenge 1: ensure that all input tensors have the same shape, except for the dimension along which they are stacked. Use the torch broadcast to function to broadcast tensors to the same shape if necessary. Challenge 2: incorrect stacking dimension, specifying an invalid or non-existent dimension for stacking will lead to an error. Sample use case that resulted in challenge 2: providing a dimension index that exceeds the number of dimensions in the input tensors. Fixes to challenge 2: double-check the dimension index to ensure it corresponds to a valid dimension within the input tensors. Verify that the dimension index is within the range of the input tensor's dimensions. Torch swapaxes. Description: the torch swapaxes function is used to swap two axes dimensions of a multi-dimensional p-torch tensor. This is useful for rearranging the data within the tensor. For example, to prepare it for a specific operation or to change the order of dimensions for visualization purposes. Inputs. Input 1: tensor, the input tensor whose axes you want to swap. This can be any p-torch tensor with at least two dimensions. Input 2: axis 1, the first axis dimension you want to swap. Input 2: axis 2, the second axis dimension you want to swap. Outputs. Output 1: swapped tensor, the output tensor with the specified axes swapped. It will have the same data as the input tensor but rearranged according to the specified axes. Output 2: none. This function doesn't return any additional values besides the swapped tensor. Steps. Step 1: the torch swapaxes function takes the input tensor and the two axes you want to swap as arguments. Step 2: the function internally rearranges the tensor's data by swapping the contents of the specified axes. This means that the elements at indices corresponding to the swapped axes are interchanged. Step 3: finally, the function returns the swapped tensor. The data within the tensor is now reorganized based on the swapped axes. Challenges and fixes. Challenge 1: invalid axis indices if the provided axis 1 or axis 2 values are outside the range of the tensor's dimensions 0 to number of dimensions 1. An error will be raised. Sample use case that resulted in challenge 1. Python. Tensor torch. RANDN 3. 4. 5. Swapped tensor torch. Swapaxis tensor. 0. 4. Error axis 4 is out of bounds for tensor of dimension 3. Fixes to challenge 1: make sure the provided axis 1 and axis 2 values are within the valid range of the tensor's dimensions. You can use tensor NDIM to get the number of dimensions and check if the provided axes are within that range. Challenge 2: confusing axis order if you are not careful with the order of axis 1 and axis 2. You might end up with an unexpected result, especially when dealing with higher dimensional tensors. Sample use case that resulted in challenge 2. Python. Tensor torch. RANDN 2. 3. 4. 5. Swapped tensor torch. Swapaxis tensor. 2. 1 swaps the third and second dimensions. Fixes to challenge 2: carefully consider the order of axis 1 and axis 2 when specifying the swap. It's helpful to visualize the tensor's dimensions and the desired swap to ensure you are swapping the correct axes. You can also use a debugger or print statements to verify the resulting swapped tensor. Torch transpose. Description: the torch transpose function in PTorch is used to swap the dimensions of a tensor along the specified axes. It essentially rearranges the elements of the tensor by interchanging the specified dimensions. Inputs. Input 1: input. This is the tensor whose dimensions you want to swap. It can be any valid PTorch tensor. Input 2: dim0. This is the first dimension that you want to swap. It should be a valid integer representing an axis index of the input tensor. Input 2: dim1. This is the second dimension that you want to swap. It should also be a valid integer representing an axis index of the input tensor. Outputs. Output 1: output. This is the transposed tensor with the specified dimensions swapped. The shape of the output tensor will be modified accordingly. Steps. Step 1: specify the tensor you want to transpose. Step 2: determine the 2 dimensions you wish to swap. Step 3: invoke torch. Transpose input. dim0. dim1 with the input tensor and the desired dimensions. Challenges and fixes. Challenge 1: incorrectly specifying the dimensions to swap can lead to an unexpected output shape. Sample use case that resulted in challenge 1: suppose you have a 3D tensor of shape 2, 3, 4 and you want to swap the first and second dimensions. However, you mistakenly provide dim00 and dim12. This will result in a tensor with shape 4, 3, 2, which might not be the desired outcome. Fixes to challenge 1: carefully verify the axis indices dimensions you intend to swap and ensure they align with the shape of your input tensor. Challenge 2: using torch transpose on tensors with more than 2 dimensions might require additional clarification about the desired transposition. Sample use case that resulted in challenge 2: if you have a 4D tensor and want to swap the first and last dimensions, you'll need to specify how to handle the intermediate dimensions. Fixes to challenge 2: for multi-dimensional tensors, consider using torch permute for more flexible control over dimension reordering. Torch swap dims. Description: the torch swap dims function is used to swap 2 dimensions in a tensor. It is essentially a way to rearrange the tensor's axes. providing greater control over how the data is organized. Inputs. Input 1. Input the input tensor whose dimensions you want to swap. Input 2. dim1. The first dimension to swap. This is the index of the dimension you want to move. Input 2. dim2. The second dimension to swap. This is the index of the dimension you want to move to the position currently occupied by dim1. Outputs. Output 1. The modified tensor with the specified dimensions swapped. Steps. Step 1. The function identifies the specified dimensions dim1 and dim2 within the input tensor. Step 2. The function rearranges the tensor by moving the data associated with dim1 to the position originally held by dim2, and vice versa. Challenges and fixes. Challenge 1. dim1 or dim2 is out of range of the tensor's dimensions. Sample use case that resulted in challenge 1. Trying to swap dimensions 3 and 5 in a tensor with only 4 dimensions. Fixes to challenge 1. Ensure that dim1 and dim2 are valid indices within the tensor's dimensions. Challenge 2. dim1 and dim2 are the same. Sample use case that resulted in challenge 2. Trying to swap dimension 2 with itself. Fixes to challenge 2. Specify 2 distinct dimensions to swap. Torch take. Description. The torch take function is a p-torch operation used to select elements from a tensor based on a given index tensor. It's essentially a way to extract specific elements from a tensor without directly manipulating indices. This function is particularly useful for implementing custom operations and for advanced indexing scenarios where you want to select elements based on a dynamic condition. Inputs. Input 1. Tensor source tensor, a p-torch tensor containing the data from which elements are to be extracted. This tensor can be of any dimension. Input 2. Tensor indices, a p-torch tensor representing the indices of the elements to be selected from the source tensor. The indices must be within the bounds of the source tensor's dimensions. Outputs. Output 1. Tensor output tensor, the resulting tensor containing the elements extracted from the source tensor based on the provided indices. The shape of this output tensor will depend on the shape and values of the indices tensor. Steps. Step 1. Torch take first identifies the elements in the source tensor corresponding to the values in the indices tensor. Step 2. These identified elements are then extracted and assembled into a new tensor, forming the output tensor. Challenges and fixes. Challenge 1. Index out of bounds. The indices tensor contains values that exceed the valid index range of the source tensor. Sample use case that resulted in challenge 1. Attempting to access elements beyond the size of the source tensor. Fixes to challenge 1. Ensure that the indices tensor contains only valid indices within the bounds of the source tensor's dimensions. Clamp the indices tensor to the valid range of the source tensor. Challenge 2. Mismatched shapes. The shape of the indices tensor is incompatible with the source tensor's shape, leading to unexpected results. Sample use case that resulted in challenge 2. Using indices tensor that has a shape that does not correspond to the intended element selection. Fixes to challenge 2. Carefully verify the shape of the indices tensor to ensure it matches the desired element. Extraction pattern. Reshape the indices tensor, if necessary, to align with the intended extraction behavior. Challenge 3. Dimensionality mismatch. The indices tensor has a different number of dimensions than the source tensor, leading to errors. Sample use case that resulted in challenge 3. Trying to use a one-dimensional indices tensor to select elements from a two-dimensional source tensor. Fixes to challenge 3. Ensure that the indices tensor has a number of dimensions consistent with the source tensor's dimensions. Use broadcasting or reshape operations to adjust the dimensionality of the indices tensor. If necessary. Torch. Take along DIM. Description. Inputs. Input the tensor from which to take elements. Indices. The indices to select elements from the input tensor. This tensor must have the same shape as the input tensor, except for the dimension specified by DIM. The values in this tensor must be within the range of the input tensor's size along the specified dimension. Output a tensor containing the elements from the input tensor specified by the indices. This tensor has the same shape as the input tensor, except that the dimension specified by DIM now has the same size as the indices tensor. Steps. Step 1. Identify the dimension along which to take elements specified by the DIM argument. Step 2. For each element in the input tensor, use the corresponding index from the indices tensor to select an element from the input tensor along the specified dimension. Challenge 1. Index out of bounds error. Sample use case attempting to access an element beyond the valid range of the input tensor along the specified dimension. Fixes ensure that the values in the indices tensor are within the range of the input tensor's size along the specified dimension. Challenge 2. Dimension mismatch error. Sample use case. The indices tensor does not have the same shape as the input tensor, except for the dimension specified by DIM. Fixes ensure that the indices tensor has the same shape as the input tensor, except for the dimension specified by DIM. Challenge 3. Invalid DIM argument. Sample use case providing a DIM argument that is out of range, e.g., negative or larger than the number of dimensions in the input tensor. Fixes ensure that the DIM argument is a valid integer within the range of the input tensor's number of dimensions. Torch tensor split. Description. The torch tensor split function splits a tensor into a specified number of subtensors along a given dimension. It divides the tensor into equal-sized chunks. And if the tensor's size along the split dimension is not divisible by the number of splits, it pads the last chunk with zeros to maintain consistent chunk sizes. Inputs. Input 1 tensor, the tensor to be split. Input 2 sections, an integer indicating the number of chunks to split the tensor into. Alternatively, it can be a list of integers specifying the size of each chunk. Input 3 DIM, the dimension along which to split the tensor. Default is 0, the first dimension. Outputs. Output 1 a list of subtensors, each representing a split chunk of the input tensor. Steps. Step 1 determine the size of each chunk. If sections is an integer, the chunk size is calculated as the length of the dimension to be split divided by sections. If sections is a list, the chunk sizes are directly specified by the list. Step 2 divide the input tensor into chunks based on the calculated chunk sizes. Step 3 if the tensor's size is not divisible by the number of splits, the last chunk is padded with zeros to match the size of other chunks. Challenges and fixes. Challenge 1 attempting to split a tensor into more chunks than its size along the split dimension. Sample use case that resulted in challenge 1 trying to split a tensor of size 4. 3 into 5 chunks along dimension 1. Fixes to challenge 1 adjust the number of splits to be less than or equal to the size of the tensor along the split dimension. Challenge 2 providing inconsistent chunk sizes in the sections list. Sample use case that resulted in challenge 2 splitting a tensor of size 6. 3 into chunks with sizes 2, 1, 3 along dimension 0. Fixes to challenge 2 ensure the sum of the chunk sizes in the sections list equals the size of a tensor along the split dimension. Challenge 3, providing a dimension value that exceeds the number of dimensions in the tensor. Sample use case that resulted in challenge 3, attempting to split a tensor of size 2, 3 along dimension 2. Fixes to challenge 3: ensure the provided dimension value is within the valid range of dimensions in the tensor. Torch, tile. Description: the torch, tile function in ptorch is used to create a new tensor by repeating the original tensor along specified dimensions. It is a versatile function for expanding the size of tensors in a controlled manner. Inputs. Input 1, input tensor. This is the original tensor you want to repeat. It can be of any dimension. Input 2, repeats tuple or list. A tuple or list that specifies how many times to repeat the original tensor along each dimension. The length of the repeats tuple or list should match the number of dimensions in the input tensor. Each element represents the number of repetitions along the corresponding dimension. Outputs. Output 1, output tensor. A new tensor with the same data as the input tensor but repeated along the specified dimensions. The size of the output tensor will be determined by the input tensor and the repeats tuple or list. Steps. Step 1, dimension expansion. The torch, tile function first expands the dimensions of the input tensor to match the length of the repeats tuple or list. Step 2, repetition. It then repeats the input tensor along each dimension according to the values in the repeats tuple or list for each dimension. The tensor is tiled the specified number of times. Challenges and fixes. Challenge 1, incorrect repeats argument. If the length of the repeats tuple or list does not match the number of dimensions in the input tensor, it will result in an error. Sample use case that resulted in challenge 1. Trying to tile a 2D tensor with a repeats tuple of length 3. Fixes to challenge 1. Ensure that the length of the repeats tuple or list matches the number of dimensions in the input tensor. Adjust the repeats tuple or list accordingly. Challenge 2, unintended dimension expansion. If you need to repeat the tensor only along specific dimensions, make sure to include 1 in the repeats tuple or list for dimensions you want to keep unchanged. Sample use case that resulted in challenge 2. Trying to repeat a 2D tensor along only the first dimension, but forgetting to include 1 for the second dimension in the repeats tuple. Fixes to challenge 2. Include 1 in the repeats tuple or list for the dimensions you want to keep unchanged. Challenge 3, memory overflow. If the original tensor and the repeats tuple or list are large, tiling might lead to a memory overflow. Sample use case that resulted in challenge 3. Attempting to tile a large tensor with high repetition values. Fixes to challenge 3. Consider using a smaller tensor or smaller repetition values. If possible, break down the tiling into smaller operations. You might need to adjust your code to manage memory efficiently. Torch, unbind. Description. The torch, unbind function is used to split a tensor along a specified dimension into a sequence of tensors. It effectively separates the tensor into individual slices along the chosen dimension. Inputs. Input 1, tensor. The input tensor to be split. Input 2, dim, optional, the dimension along which to split the tensor. If not provided, it defaults to 0, the first dimension. Outputs. Output 1, a sequence of tensors, each representing a slice of the input tensor along the specified dimension. The number of tensors in the sequence is equal to the size of the input tensor along the specified dimension. Steps. Step 1, identify the dimension along which to split the tensor. If not specified, The default is the first dimension dim0. Step 2. Extract slices of the input tensor along the chosen dimension. Each slice becomes a separate tensor in the output sequence. Challenges and fixes. Challenge 1. Incorrect dimension specification. Sample use case that resulted in challenge 1 splitting a tensor along a dimension that does not exist or is beyond the number of dimensions in the tensor. Fixes to challenge 1 ensure that the specified dimension is within the valid range 0 to the number of dimensions in the tensor 1. Challenge 2. Understanding the output format. Sample use case that resulted in challenge 2 difficulty interpreting the sequence of tensors returned by torch. Unbind. Fixes to challenge 2 recognize that the output is a sequence of tensors, each representing a slice of the original tensor. The order of the slices corresponds to the order of the elements along the specified dimension. Torch. Unravel index. Description. This function converts a flat index or a tensor of flat indices into a tuple of coordinate tensors. For a given shape, it essentially performs the reverse operation of torch. Ravel multi-index. Inputs. Index a single integer or a tensor of integers representing the flat index or indices. Shape a tuple or a tensor specifying the shape of the multi-dimensional space from which the indices are derived. Outputs. Output a tuple of tensors, each containing the corresponding coordinate values for each dimension of the multi-dimensional space. Steps. The function iteratively calculates the coordinate values for each dimension by repeatedly dividing the input index by the corresponding dimension size and taking the remainder. The quotient from each division becomes the new input index for the next iteration, while the remainder is stored as a coordinate value. Challenges and fixes. Challenge 1. Incorrect input shape. Sample use case that resulted in challenge 1 attempting to unravel an index that is larger than the total number of elements in the specified shape. Fixes to challenge 1 ensure that the input index is within the range of valid indices for the given shape. Challenge 2. Incompatible input types. Sample use case that resulted in challenge 2 passing a tensor of indices that has a different data type than the shape tensor. Fixes to challenge 2 use the same data type for both the input index and the shape tensor. Challenge 3. Mismatched dimensionality. Sample use case that resulted in challenge 3 providing a shape tensor with a different number of dimensions than the number of coordinates required for the input index. Fixes to challenge 3 ensure that the number of elements in the shape tensor matches the number of coordinates needed to represent the input index. Torch and squeeze. Description. The torch and squeeze function adds a new dimension to an existing tensor at a specified position. It's useful for aligning tensor shapes during operations like broadcasting or concatenating. Inputs. Input 1 tensor, the input tensor to which you want to add a dimension. Input 2 dim, the position index in the tensor where you want to insert the new dimension. Outputs. Output 1 tensor, the modified tensor with the added dimension. Steps. Step 1 torch and squeeze takes the input tensor and the desired dimension index dim as arguments. Step 2 it inserts a new dimension of size 1 at the specified index, effectively expanding the tensor's shape. Challenges and fixes. Challenge 1 incorrect dim value. Sample use case if you try to insert a dimension at an index outside the valid range of the tensor's shape, you'll get an error. Fixes to challenge 1 double check the dim value to ensure it's within the bounds of the tensor's dimensions. Challenge 2 understanding the output shape. Sample use case. It can be confusing to determine the output shape of the tensor after applying n-squeeze. Fixes to challenge 2. Carefully examine the output shape of the tensor using tensor shape 2. Ensure it aligns with your expectations. Torch V-split. Description: the torch V-split function is a p-torch operation that splits a tensor into a specified number of chunks along the vertical axis dimension 0. It divides the tensor into equal-sized chunks if the size of the tensor is divisible by the number of splits. If the size is not divisible, it distributes the remainder across the chunks. Inputs. Input 1 tensor. The input tensor to be split along the vertical axis dimension 0. Input 2 size. An integer specifying the number of chunks to split the tensor into. Outputs. Output 1 a list of tensors, where each tensor represents a vertical chunk of the input tensor. Steps. Step 1 the function determines the size of each chunk by dividing the number of rows in the input tensor by the specified number of splits. Step 2 the function splits the input tensor into the specified number of chunks along a vertical axis, creating a list of tensors. Each tensor in the list represents a vertical chunk of the original input tensor. Challenges and fixes. Challenge 1 input tensor size is not divisible by the specified number of splits. This will result in unequal sized chunks. Sample use case that resulted in challenge 1 splitting a tensor with 7 rows into 3 chunks. Fixes to challenge 1 the function will distribute the remainder rows across the chunks, resulting in chunks with different sizes. For instance, splitting a tensor with 7 rows into 3 chunks would result in chunks with 2, and 3 rows, respectively. Challenge 2 input tensor has more than 2 dimensions. The V-split function is designed for splitting tensors along the vertical axis dimension 0. If the tensor has more than 2 dimensions, the function will split the tensor along the first dimension only. Sample use case that resulted in challenge 2 splitting a 3-dimensional tensor with dimensions 5, 3, 2 into 2 chunks. Fixes to challenge 2 the function will split the tensor along the first dimension only, resulting in 2 tensors with dimensions 2, 3, 2 and 3, 3, 2, respectively.